Hey, how are you all doing? All right, give it another 2 minutes. What do we got? 1, 2, 3, 4, 5, 6, 7, 8. We got eight of you. My guess is we'll get 2 more in the next 2 minutes. So let's just wait. All right, there we are. Yay. You guys have your video on. Awesome. Okay, let's let me get organized here and we'll jump into it. My plan for today is to kind of just go through what I think are the highlights of chapter 4. I'm not going to hold you responsible for any of the material in chapter 4, but it's interesting material, and I will show you some videos, and there's some
We're good with the standing desk for
engineering applications. So I think it's worth seeing and worth just going through real quick. It's all within kind of the realm of stuff we've done, but there's an added twist to it. And there's some super interesting results that have been historically important. And if any of you are thinking about engineering or any related field, those are the results there are important and worth knowing. And if any of you are musicians, there are some things that affect the theory of music in chapter 4. It's really kind of fascinating material. So I thought I'd just go through that today, and Wednesday will be more review. Wednesday I'll distribute the take-home final, and you'll have about a week to do it. I think that's it. Are there any questions? Oh, that the final, I know you asked me what material to study for the final. It's going to be almost exclusively on chapters 3 and 5. So I would just go through chapters 3 and 5. Chapter 3 again was linear systems. So understanding phase portraits of linear systems, eigenvalues, eigenvectors, and all that, but everything's linear, so you just have a single equilibrium point at the origin. So there's the trace determinant plane, all of the pictures that you can get with saddles, sinks, sources, spiral saddles, spiral sinks, spiral sources, all that. And then chapter 5 was on nonlinear systems, and essentially you just find all the equilibrium points and then linearize around each equilibrium point. That was like the first 2 sections of chapter 5. And then you can add to that picture the null clines, help you kind of fill in the rest of the phase portrait. That was also chapter 5. And then in chapter 5, we also looked at 2 very specific kinds of systems, which are the Hamiltonian and the dissipative systems, which have specific kinds of phase portraits that, again, help you just draw the picture and understand the behavior of those systems. We ended chapter 5. We did the second to last section, was the last thing we did in chapter 5. And that was the 3-dimensional systems that we talked about last time. And that's, I think, interesting material, but I won't put that on the final because it would be hard to ask questions of you for 3-dimensional systems. Okay, any questions on that?
Is the test going to be open notes?
Yes. Open notes, open book. Um, I'm just going to ask you to refrain from Googling things, refrain from using Wolfram Alpha. Just I'm going to try to write an exam where all the calculations are doable by hand. So you shouldn't need a calculator or Wolfram Alpha or anything like that. Um, so you can consult your notes and the book, but I would just ask you not to use any other resources besides those. Other questions?
I have a quick question. What
Yeah.
does like the Pitzer policy mean for like non-Pitzer students?
Yeah, good question. So it's a really good question. To be honest, I'm not 100% sure of the answer. Um, I think what's going on is that each college has now passed its own policy on grades. I know Scripps passed a different policy last Thursday, I think. And what's going to happen as instructor for each class is that everyone has a drop-down menu where we assign grades to each student. And for each student, our drop-down menu will look different. So my drop-down menu for the Pitzer students will just say pass or fail. And my drop-down menu for Pomona students might just be letter grade options, and pass-fail may not even be an option. I don't know. I don't remember what Pomona's policy is. So in some sense, I don't need to know the policy for each college because I'm just going to have a limited number of choices for each student. I know the Pitzer students, I think the only options at this point are going to be pass or fail. The default option, I moved this class to pass fail by default for everybody. So that was up to, I think all 5 colleges agreed that that was a choice that the instructor could make kind of early on. But if any of you prefer a letter grade, then if you're not a Pitzer student, I think a letter grade is an option. And that was left up, for most of the colleges, that was left up to the student. So I've moved you all to pass fail, but if you would prefer a letter grade, you're going to have to email me and ask for that. And give me some kind of compelling reason, because I actually think in the interest of fairness to everyone, it would be better if everyone just agreed to get a pass fail grade. But I understand there are some specific considerations for some of you where you really need a letter grade for maybe an outside scholarship, or there are some international students who will lose their visas if they are not on a letter grade. I mean, there were some crazy stories we heard why some people actually really do need a letter grade. So just email me those reasons, and I'm going to try to compute letter grades for all of you. Even for the Pitzer students, some of you, I had some concerns in one of my other classes that for future employers, things might look weird on their transcript. So they asked me if I would be willing to write them a letter in the future that says they would have gotten a certain grade, and I'd be willing to do that for all of you. It's fine. I'll try to record a letter grade for each of you in my grade book. And so I can then look back at that in the future if you ever need it.
Will we know what grade we would have gotten even if a pass is put in the portal?
You can ask me. Yeah. I'm not planning to just like distribute that to everybody, but if you want to know what you would have gotten, then I'll let you know. Yeah, I think some of the colleges are giving their students the option to switch to a letter grade or to make that decision fairly late, after finals. So yeah, if you want to know, just ask me and I'll let you know. Okay, other questions on that? We good? All right, let's jump into chapter 4. Actually, chapter 4 I think is interesting. I think we'll do some interesting, fun things today. It's kind of a fun chapter. If you read through the chapter, it seems anything but fun. It's kind of dry, and there's a whole lot of like dry calculations. But I'm just going to try to hit the highlights, which I think are interesting and worth going through. And I think you'll learn some things that might interest you. So it's all about harmonic oscillators. But in chapter 4, it's forced harmonic oscillators. Oh, you don't see my screen. Hold on, let me share my screen. Okay. So chapter 4 is all about, oh, sorry, let me rearrange my windows here. All right. Okay, we're all set up now, almost all set up. There we go. All right, it's all about forced harmonic oscillators. So we've seen the spring a bunch of times. It's been kind of one of our prominent examples of a differential equation where we have this kind of modeling scenario. We have these physical constraints. So we have some mass and there's a spring. And we've talked about the physics that are going there. We've talked about there's a velocity term, a friction term, and in the end, the differential equation that you get is just a standard second order differential equation with constant coefficients. So you get d squared y, d t squared plus something, they use the letter p in this chapter, dy dt plus something times y equals 0. So that's just kind of the standard equation for a harmonic oscillator, just something that oscillates back and forth, a mass on a spring. And I think we derived that equation assuming no friction, and it's that second term in the middle that's the friction term. Friction is proportional to velocity, so it just adds a little bit to that equation. Okay, so we've already seen this equation a number of times. What's new in this chapter is instead of 0 here, we make this a non-autonomous system by adding some function of time. And that function of time is supposed to represent energy being put into this system, either just a constant amount of energy, so you're just adding some energy to this system the whole time. So you would expect the oscillations to just get bigger and bigger and bigger and oscillate out of control because you're just constantly adding more energy to that oscillating mass. Or that function could be a periodic function. So you're just periodically giving that mass a little kick, okay? So if you think of it, if this were a mass on a pendulum, you're just giving a little kick each time, okay? And then we can ask, well, how does that affect the solutions? What happens there? And we haven't learned very many techniques at all for non-autonomous systems, right? When there's a T term, then none of the stuff we did in chapters 3 or 5 are going to give us the complete solution. But it's almost a linear system. And chapter 4.1 starts on like the second or third page with something called the extended linearity principle. Okay, so the extended linearity principle says, you can find the solution by doing two things. So step 1, find solution of the unforced system. So the unforced system is the one where this is 0. F of t is called the forcing function. So the unforced system means the forcing function is just 0. Right? Step 2. So that's just a linear system now. It's second order. So you have to convert it to a first order system, which we did in chapter 3, and then do everything we did in chapter 3, and you might have a spiral sink, spiral source. I mean, who knows what you're going to get there? It depends on those coefficients for P and Q. The second step, and this is the hard step, is to find, this is to find the general solution. This is to find one specific solution of the forced system. And then the third solution is third step, the general solution of the forced system is the sum of those two things. It's 1 plus 2. Just add those. So you just find one specific solution of the force system and all solutions of the unforced system and add them, and that gives you all solutions of the force system. Right? Now, step one is something you should all be able to do. Okay, that's what we did in chapter 3. It's step 2 is like, how do you find even just one solution of this system? And in chapter 4, they say, well, you can do that just by guessing, and here's how you guess. Here's how you make those educated guesses. And I'm not going to go through every possible case they go through for how they make their guesses. I'm just going to show you 2 cases where the guess is very similar in both cases, and it's a relatively simple guess, and it's a guess you yourself might have made to begin with. Okay, so we're going to go through just 2 examples and be done. Okay, but those 2 examples I think will be very illustrative of kind of what can happen in general. Right? So let's go through it. So the first system we're going to start with, this is the system it's on. If you want to follow along, it's the system on page 394 of the book. So it's t squared y t squared plus 5 ty dt plus 6y equals, and the forcing function is e to the minus t. Okay, so step 1 is to just replace that e to the minus t with a 0 and find the solution, find the general solution of that unforced system. So we'll go through it. Step 1 is solve t squared y t squared plus 5 ty t plus 6y equals 0. All right, now you all should be experts at this point. So you're going to talk me through it, okay? What do I do? How do I solve a system like this? Sorry, an equation like this, second order equation like this?
You can introduce a second variable.
Yep, introduce second variable. So let's call it v, right? And v is supposed to represent the velocity, so dy dt equals v. Okay, which means dv dt is what? Might help to rewrite this.
Oh, you just need to move all the stuff that's not the second derivative to the other side.
Yeah, the equation becomes dv dt e plus 5v plus 6y equals 0. So dv dt is minus 5v minus 6y. How would I write that as a matrix? Be a little bit careful there. What matrix is it?
Zero,
Good,
1, -5, or -6, -5.
good, perfect, good. All right, what's the next step?
Take the determinant. Oh, characteristic polynomial.
Characteristic polynomials, 0 minus lambda times minus 5 minus lambda minus -6 equals 0. So lambda squared plus 5 lambda outside, inside, last, that's it, plus 6 equals 0. That factors nicely. Lambda plus 2 times lambda plus 3 equals 0. So lambda equals minus 2 power minus 3. Next.
Eigenvectors.
Eigenvectors. Good. Well, remember we're doing, did anybody remember how this worked? Well, okay, sure. Yeah, eigenvectors. Let's find the eigenvectors. We might as well. It's not going to really matter. Let's say V1 is the eigenvector corresponding to -2, and V2 is the eigenvector corresponding to -3. Okay, then the general solution would be what? Y, V would be K1 V1 times e to the -2t plus K2 V2 times e to the -3t. That make sense? Okay, now the original equation all the way back here didn't have a v in it. So when you are asked to solve that equation, you're just asked for a function of y. Okay, so y, let's say just for argument's sake, let's say v1 was 2, 3, and v2, I'm just pretending this was -1, 1. Okay, then what we get here is k1 times 2, 3 e to the -2t plus k2 times -1, 1 times e to the -3t. Now, what's the y function by itself? You should be able to rewrite that as two separate functions, right? The first one's y, the second one's v. So what's the first one? Michelle, you're nodding. Tell me the y function.
Y is equal to k 2 times k1 e to the -2t minus k2 e to the -3t.
Okay, good. Now, the point is that k1 and k2 are just arbitrary numbers, which means 2 times k1 and -1 times k2 are just arbitrary numbers. So the general solution, we don't even have to write the 2 and the -1. It's just k1. It's just some number times e to the -2t plus some other number times e to the -3t. We never actually have to solve for v1 and v2 if we just want the general solution for one of those functions. Everybody understand why the v1, whenever we have to do that work to find v1 and v2? Okay, cool. All right, that was step one. Step one, find the general solution of the unforced system. Done. Okay. Step two was to find one specific solution of the forced system. So again, we've got d squared y dt squared plus, was it 5 and 6? 5, yeah. 5 dy dt plus 6 equals e to the -2t, -2. All right, so here's the guess that they suggest. They suggest looking at this function, the forced function on the right, and using that as their guess. E to the -t as our solution for y. And what you find when you do that is that you're off by a constant. So a more general guess, so the first guess they suggest is e to the -t. And when you plug that in, you find it's wrong, but it's off by a constant. So then they say, okay, well, then let's figure out what the constant has to be so that we're not off by a constant. So this is called it's called the method of undetermined coefficient. So you make this educated guess, and your educated guess has this undetermined coefficient. Then you plug it in and figure out what that undetermined coefficient has to be. Okay, so in this case, A is the undetermined coefficient. We're going to figure out what A is, and that's going to allow us to find one specific solution that'll work. Right? So the only thing fishy here is, well, how did they ever know to guess e to the minus t to begin with? And that's just, that's actually chapter 7. So if we were to have had time to go through chapter 7 shows you ways to do a problem like this without guessing at all. But I think they wanted to kind of work in some interesting stuff here in chapter 4, so they're going to just present this as an educated guess. So let's go through it. So let's figure out what A is in this case. So we're going to just plug this into Y here and here, and then we'll get an equation for A. So if Y is A e to the minus t, then what is the second derivative of Y? What's the first derivative?
Negative a e to the minus t.
Good. Now what's the second derivative? What's the derivative of that?
A e to the minus t.
Good. You just get another negative sign. Perfect. Okay. Plus 6. Oops, plus 6. I have a y here. Plus 6y. And that gives us, again, a e to the minus t. Okay, so that's sweet because we get an e to the minus t everywhere. So we got a e to the minus t minus 5a e to the minus t plus 6a e to the minus t, which is 2 a e to the minus t equals e to the minus t. Did I do that right? 6 plus 1 is 7, minus 5 is 2. You can divide both sides by e to the minus t, and we get a has to be 1/2. Okay, so there we go. There's a specific solution. It's 1/2 e to the minus t. So we found the general solution of the unforced system. And by guessing, we found a specific solution of the forced system. So the general solution of the forced system is just the sum of those two. So general solution is k1 e to the minus 2t plus k2 e to the minus 3t plus 1/2 e to the minus t. Some things to notice here is e to the minus 2t and e to the minus 3t die off a lot faster than e to the minus t. So they just qualitatively understanding what's going on here. If this is the graph of, let's see, let me color code these. Let's say this is the graph of e to the minus 1/2 e to the minus 2t. It's just some negative exponential. Okay, then any other function, you start off adding something, but then eventually that term dies off much faster than e to the minus t, and it becomes asymptotic to that 1/2 e to the minus 2t. So other solutions eventually converge to the same, they're asymptotic to 1/2 e to the minus t. So the general solution ends up converging to that specific solution that we found. Okay, so that's what happens when the forcing function is a negative exponential. So the forcing function itself dies off. Everybody follow that? This is not very insightful or terribly interesting. Just wanted to make sure you understood the algebra.
Professor, I had a question.
Yeah.
When you say the general solution, what is that the general solution to? Like, what is that whole thing equal to?
That's the general solution of the original equation of this thing.
So that whole thing is equal to e to the negative t, or like,
E to the minus t is just one half e to the minus t is a specific solution when k1 and k2 are 0. But if you want the set of all solutions, then k1 and k2 can be anything.
oh, okay, yeah, okay, I get it.
That
Thank
makes
you.
sense? Yeah. And we found the specific solution before we found the general solution, but we got the general solution just by adding them.
Okay, thank you.
Sure. Yeah, remember k1 and k2 can be anything. So if you set them both equal to 0, you just recover that one specific solution that we just found by that method of undetermined coefficients up here, this stuff. All right, a system where you have a harmonic oscillator and you're constantly adding energy to that system is actually not very common in real world. In the real world, there are lots and lots of examples, though, where you're adding energy to the system periodically. So we're going to look at a simpler system where there's no friction term, but the forcing function is going to be a little more realistic. Because it's going to be a sinusoidal forcing function where you're just periodically adding energy to the system. So this is section 4.3 of the book. It's the first example in section 4.3. And the first example they give, and this is really going to be illustrative of everything that's going to happen, is d squared y dt squared plus, there's going to be no friction term, so no dy dt term, 2y, and the forcing function, instead of being an exponential, like e to the minus t like we just had, it's going to be a sinusoid, cosine of omega t. And you should think of omega as just some constant, which is the frequency of the forcing. Whoa. So the larger omega is, the higher the frequency. So for those of you who remember your high school physics, when you have a high frequency forcing, it just oscillates more and more and more and more frequently. If you have a low frequency oscillations, right, then the period is greater of those oscillations. Period and frequency is just one is the reciprocal of the other. So low frequency means you have a long period of waves that are really spaced apart. High frequency means the waves are really close together. Okay, so omega is the frequency there. It's the frequency of the forcing. Okay, so let's see what happens when you have some forcing. So again, there are two steps here. The first step is to find the general solution of the unforced system. And the second step is to find a specific solution of the forced system, and then the general solution of the forced system is going to be the sum of those two things. Good? All right. So let's do step one, which is to find the general solution of the unforced system. So we got to set up d squared y dt squared plus 2y equals 0. And again, the way we're going to do that is by introducing another variable, dv dt. Oops, that's not right. We'll set up another variable v, so that dy dt is v, and that makes dv dt equal to what? Easy in this case.
Negative 2y.
Yeah, just minus 2y. And dv dt is then d squared y dt squared, which is right here. So you just bring the 2y over to the other side. And we can write this as a matrix. This is the matrix 0, 1, minus 2, 0. Okay, easy enough. Characteristic polynomial. We have lambda squared minus negative 2 equals 0. So lambda equals plus or minus root 2i. All right, who remembers what to do when you have an imaginary eigenvalue? Oh, again, you know what? Again, it doesn't matter, right? The next step, if it was a system of two equations, the next step would be to find, to just pick one of those, say lambda equals root 2i, find the complex eigenvector. So v would be some complex eigenvector. So let's just sort of pretend that this is the vector 2 plus I and 3 minus 2i or something. I'm just going to pretend here, right? So then the general solution, sorry, specific solution would be 2 plus I, 3 minus 2i. Again, I'm just reviewing here. I'm partly doing this to review, times e to the root 2it. That's one specific solution. Now, what do we do? How do I get two? To get the general solution, we need two real solutions. We have one specific complex solution. We got to break that up into two real solutions. Anybody remember what to do?
Do you use Euler's?
Yeah, Euler's formula, right? So first of all, we can write this as 2, 3 plus I times 1 minus 2. Okay, and then we can write that as cosine root 2t plus I times sine root 2t. Okay, and all of this is equal to yv. You know what? I like the idea of reviewing. We don't necessarily need to go through all of this, but let's do it as a review. Okay, this is chapter 3 stuff. Let's go back. Let's actually, I just made up some random complex numbers. Let's actually do it. Let's find the eigenvector and let's really do it, because this will be a good review for the final. Sorry, those of you trying to take notes. Sorry, let's actually figure out the eigenvector and let's really do it. So let's pick this eigenvector square root of 2i, and we have this matrix 0, 1, minus 2, 0. It's an easy matrix. 0, 1, minus 2, 0 times yv should equal root 2i times yv. Okay, and that tells us we get two equations out of this. We have that v equals root 2i y, and we also get the equation minus 2y equals root 2i v. Okay, both these are going to be redundant equations, so let's just look at that first one. So what eigenvector do we get? If y is 1, then v has to be root 2i. Good? Is that okay? You remembering this? This is like stuff we did a month ago, right? So now we're going to write down v e to the lambda t. So that's 1 root 2i times e to the root 2i t. Okay, let's keep going. That is 1, 0 plus I times 0 root 2 times cosine of root 2t plus I sine root 2t, right? There's Euler's formula right there. Okay, let's FOIL that out. So first outside, inside, last. So we get 1, 0 cosine root 2t. First outside term is I times 1, 0 times sine of root 2t. Inside terms are I times 0 root 2 times cosine of root 2t. And the last term, so we're going to get an I times I is a minus 1, 0 root 2 sine root 2t. Stop me or slow me down if I lose you. Okay? All right. So now we get, what do we get here? We get, we get a real solution, cosine root 2t and minus root 2 sine root 2t. That's from the first term and the last term. I just combined them to give me this vector. And then we have an I for the other terms, and we get sine root 2t and root 2 cosine root 2t. That's one specific solution of the unforced system. Now, does anybody remember how we get the general solution from that?
You just add scalars, right? And
Yeah, you take the real part and the imaginary part, and you do any linear combination of those. So the general solution will be k1 times cosine root 2t minus root 2 sine root 2t plus k2 sine root 2t root 2 cosine root 2t. Okay, and that is the general solution of the unforced system for y and v. Now again, we just want an answer for y. So y of t equals k1 cosine root 2t plus k2 sine root 2t. And again, we actually didn't have to find the eigenvectors to get that far. Just knowing in advance, we would have gotten something times cosine plus something times sine. And those somethings are going to be multiplied by arbitrary constants. So I think it was useful to work through this as a review, but we didn't need to do the eigenvector step to get to this point. If we're just interested in that y function, we knew we were going to get something times cosine plus something times sine. Got it? Okay, so this is the general solution of the unforced system.
Professor,
Yeah.
I had a question. Why is it that we only have to look at one of the eigenvectors to know?
Yeah, good. No, that's a great question. Because there's theorem that says if you have a two-dimensional linear system, then all you need to find is two solutions. And one eigenvalue ends up giving you two solutions, so we never ended up needing to look at the other eigenvalue. Yeah, there's this kind of like amazing thing that really helps, that cuts our work in half. Yeah. This is a good question. All right, so here's the general solution of the unforced system. And then step 2 is to find a specific solution of the unforced system. So let me just remind you of a specific solution of the forced system. So let me just remind you what the system is. It's d squared y dt squared plus 2y equals cosine omega t. All right, now, if we had e to the minus t here instead, like in the last example, the first example we did, then we would have guessed something like a times e to the minus t as a solution. Yep. That's what we did the last time. If we had e to the minus t on the right, then the guess that makes sense is to guess a times e to the minus t here. All right, but we don't have that. You can try guessing a times cosine of omega t, and that doesn't work. So here's what you can do. The trick is to, again, remember Euler's formula and rewrite the right side in terms of imaginary numbers. This is the real part of e to the I omega t. So when we have an exponential, we're going to guess some undetermined coefficient times that exponential. So from this perspective, then we're going to guess y equals a times e to the I omega t. All right, so rewriting the cosine as an exponential with Euler's formula kind of informs us what our guess should be. And it looks a lot like our guess from our previous example. Right? Whenever you have the forcing function as an exponential, then you just guess some scalar times that exponential. Everybody see what happened here? Right? We rewrote the cosine as an exponential. It's a complex exponential now. And so that informs us as to what our guess should be, which is just a scalar times that exponential. All right, so let's work through it now. Let's see if we can figure out what a is by plugging it into this equation. So, let's just plug it into a simpler equation. Let's plug it into the equation d squared y dt squared plus 2y equals e to the I omega t. Let's plug this here and here and see what happens. Okay, so what is the first derivative? What happens when you take the derivative once? Or just jump to it. Just tell me the second derivative. What's the second derivative there?
Is it a times I squared omega squared e to the I omega t?
Yep. Now what's I squared?
-1.
Good. So we get negative a omega squared e to the I omega t. Good. Perfect. Everybody see where that negative sign comes from? Because we have an I squared, which was a -1. Good. All right. So we can divide everything by e to the I omega t. And now we just get 2a minus a omega squared. Oh, it's minus, yeah, I just switch the terms, equals 1. So a times 2 minus omega squared equals 1. So a equals 1 over 2 minus omega squared. Okay, now remember that we're really interested in the real part of a e to the I omega t. So we want the real part of 1 over 2 minus omega squared of e to the I omega t. The 2 minus omega squared is just a constant. So that's 1 over 2 minus omega squared times the real part of e to the I omega t. And we already said the real part of e to the I omega t is just cosine omega t. Right, this was our guess for y. So this is one specific solution of the forced equation. Okay, so we have the general solution of the unforced equation way up here. Okay, and then a specific solution of the forced equation down here. And that allows us to give us the general solution of the forced equation, which is the sum of the two. So it's k1 times cosine root 2t plus k2 sine root 2t plus, plus 1 over 2 minus omega squared cosine omega t. All right, good. All right, so now we fire up any kind of computer graphing program, and I'm already getting a little bit low on time because there are some videos I want to show you. So I'm just going to sort of copy what's in the book. So in the book, they show you some solutions, what this looks like if you were to graph it for different values of omega. One thing that's interesting is when omega is near square root of 2. What happens if omega equals square root of 2 with this equation? Just look at that equation. And what goes wrong if omega equals square root of 2?
There would be some type of discontinuity.
Yeah.
It doesn't exist.
Yeah, we get a 1 over 0 right here, right? So it's got to be discontinuous. So one of the things to do to try to understand this is to look at the limit when omega approaches square root of 2. The algebra is different. They go through in one of the sections of the book, they go through that you can do some different algebra to understand what's happening when omega actually equals square root of 2. You can get a solution in that case. You just have to do the algebra differently. But the picture you end up with is the limiting picture of what happens as omega approaches square root of 2. So let's see what happens when omega is near square root of 2, like 1.2. And they show this picture. It's a beautiful picture. It looks like the following. So it looks like there's a sort of sinusoid. Try to draw this carefully. And if you look at its negative, the actual solution oscillates between those. Like that. So you have these sort of two oscillations. They're the high frequency oscillations, and then there's a lower frequency oscillation that's sort of superimposed on that. And those low frequency oscillations, the dashed lines, those are called the beats. So if any of you play guitar and you've learned how to tune your guitar by ear, you should be familiar with this. And I happen to have a guitar behind me. And I don't know if I'm going to be able to do this. I haven't tried in a while. But when you all hear that? Okay. Those two. So if I hold my finger here, and sorry, you can't see. If I hold my finger right here, down here on the 1, 2, 3, 4, 5th fret, and pluck that string where my finger is, and pluck the next string down, those should be the exact same note. Okay, they should sound the same if the guitar is in tune. Now I'm going to intentionally throw this guitar out of tune. So they're close, but they're not the same. I just tweaked it a little bit. Oops. I don't know if you all can hear that. There's a wow, 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 wow. The closer I get, This is how you tune a guitar by ear. As you listen for those beats and you keep tweaking the tension until the beats disappear. So when that frequency is close, you can really hear this beating phenomena. Now, one thing that's really crucial to understand is what happens as omega approaches square root of 2. And what you see is that the period of the beeps goes to infinity, and the amplitude goes to infinity. Okay. So if omega was a little bit closer to 1.2, let's say omega were 1.21, and square root of 2 is 1.4 actually. So let's say I used 1.3. The picture might look more like this. Sorry, that's a terrible picture. Now I'm kind of rushing, right? And as omega gets closer and closer to square root of 2, now the amplitudes and in the limit, really what you're seeing is this picture. See what happens as this peak and this peak go that way and that way, then what you're seeing is just this initial part of the picture just getting bigger and bigger and bigger. Okay, and that's called resonance. So as an engineer, you sometimes have control over what omega is. And there's this one value of omega that's super bad. Any other value is fine. You'll just get this beating phenomena. But if you pick this one bad value of omega, that's called the resonant frequency of the system, then your solutions are going to go off to infinity. Then you get this picture. This bad value of omega gives you this horrible picture where the oscillations get bigger and 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 bigger. Okay? And that's super bad. You never want to design a system where your oscillations grow exponentially. Okay? And just as a really visual, so now I'm going to play some videos of some famous examples where you have these resonant frequencies. And you can see things get ugly. So let me find them. I pulled them up earlier. Oh yeah, here we go. So there's a recent example and a classic example. So first I'll play the kind of classic example. I've got to share my screen. Well, you share desktop too. Okay, so this was the Tacoma Narrows Bridge. Everybody seeing that? It says gale causes bridge to sway. All right, this is a more complicated system. It's clearly not a mass on a spring. And they go through, in the last section of chapter 3, they talk about the Tacoma Narrows Bridge. And they go through a more sophisticated model. But the idea is that even in this more complicated model, there's still resonance. So, and things can cause resonance, which are when you add vibrations to a system, it causes resonance. So in this example, you've got this suspension bridge. I'll start playing the video. And what's happening is the wind blew. This was shortly after the opening of the bridge. So they built this bridge up in Washington State, and the wind starts blowing, and that wind is adding resonance to the bridge. So you see these oscillations, and The problem with resonance is the oscillations get bigger and bigger and bigger and bigger and bigger. I think this is a 1-minute video. Oh, it's a 5-minute video. I'll speed it up. There's one poor idiot left their car on the bridge and they abandoned their car. And you can see there's even a person. Do you see this? There's a person who got out of the car and was running down the bridge. Can't see, it's a very poor quality video because it's very old. This happened in, I want to say like the 1920s or something. This is a colorized version. It was not, this was before color film. They keep oscillating. See, these oscillations are just getting bigger and bigger and bigger and bigger because that wind just kept blowing and blowing and blowing and hit that right resonant frequency. There's one of the supports you could see just going side, just wiggling side by side by side by side. You see that car up there? There's a car right over here on the top. Oh, and there's the person right over here on the right. As they get closer, they'll be a little clearer. The video quality is super bad. You could see him walking toward the camera and just trying to keep his balance. Yeah, and as you would expect, if those oscillations get bigger and bigger and bigger, then it's just not going to be able to handle it at some point. And this was shortly after the bridge opened. The whole thing just collapsed, just broke. Couldn't take it anymore.
So, was this a flaw by design, or was it just unlucky that the wind caused it to hit the right frequency that we're talking about?
Well, I think both. I mean, the point is that the engineers didn't account for the fact that the wind might hit that resonant frequency.
Okay.
So you can call that a flaw by design, but also there was a very specific frequency that wind happened to hit. So when modern engineers design a bridge, they know that this can happen, and they do things to protect against any possible resonant frequency. Or so you would think. And that brings us to our next video, which is the Millennium Bridge opening. This happened in the year 2000, not very long ago. In the year 2000, they built the first bridge in 100 years over the Thames River in London. And on opening day, it was packed with people. It's a pedestrian bridge. It was packed with people walking across this bridge. And I'll leave the audio on because you can kind of hear what happened. It's a different kind of bridge. It's not a suspension bridge. It's more of a tension bridge. You can see the tension rods on the sides. So it's not subject to vertical oscillations, but it is subject to horizontal oscillations. And what happened is just natural vibrations of the bridge started kind of reinforcing themselves. And as the people were walking across, they said they had to kind of spread their legs and kind of do this sort of side to side shuffle to keep their balance. But everybody had to do the exact same thing. So what happened was all the people on that bridge ended up kind of marching in unison. And it was the people themselves on that bridge that hit this resonant frequency. You can see in a minute, you see all the people there? They're all like swaying back and forth in unison. Let's go back, no. There's this great, little clip at the end where all the people there just in unison, just swaying back and forth. And again, it's just another example of resonance where, and you would think by the year 2000, the engineering would have been advanced enough to account for this, but they didn't expect like there'd be so many people on the bridge and that they would all end up in kind of lockstep with each other to account for these vibrations. And that effect of the people going back and forth would reinforce more vibrations, which would reinforce more people swaying back and forth. And you get this exact phenomena of resonance. So, from an engineering perspective, it's super important to understand resonance. One other example, I wish I had it with me, is if you've ever blown into a glass jar, like have you ever heard a jug band? Take a giant jug, like an apple cider jug or something, get a big old glass jar, or even like a water cooler jug, and blow in the top of it. And if you blow at just the right speed, you'll hear the jug making this noise, playing a note. You could actually play an instrument, the primitive instrument that way, basically a one-note instrument, by blowing into the top of a jug or a bottle, a big enough bottle, you can hear this. And that, again, that's another example of resonance. You have to blow at just the right speed so that you set up resonance inside the jar, and then that makes the air vibrate enough that you can then hear it. Right? So understanding these phenomena of beats and resonance are really important in music theory, and all instruments are in some sense based on these different phenomena of what happens when you have oscillators and you're adding energy to the system at different frequencies, either by plucking strings, or if you play a wind instrument, you're adding energy to the system by blowing on a reed or whatever. So I don't know. I just thought you can't end a differential equations class without covering resonance and beats, and you should have all seen this at some point. So I'm glad we had a chance to do it, to talk about it. Again, this is all chapter 4 of the book. They do go through the Millennium Bridge as an example. This book was published after the Millennium Bridge, so they at the end of 4.4, they do discuss the Millennium Bridge. And then in the last chapter of the book, they do talk about the Tacoma-Narrows Bridge and a more sophisticated model. But the point's the same, is that even in that more complicated model, there is this phenomenon of resonance that you see. The disturbing part of chapter 4, as I said, is that it involves this guessing method, which I never like, because I don't like the idea of students having to remember what to guess. Just for your own benefit, if you want to go further and do some more research, especially if you're an engineering student, I would read chapter 7. Chapter 7 goes to this idea of Laplace transforms. It's some more sophisticated mathematics that involves doing a few integrals to help you kind of set things up. But once you go through that mathematics, you no longer have to guess. There are ways to take the guesswork out of this and go back into the material in chapter 4 after you've done chapter 7 and realize you never had to do any guessing at all. All right, so Wednesday we'll do a review. Wednesday we'll do also, I think I'll pause at some point to do course evaluations. I'm not sure how course evaluations are going to work this semester because they're all online. So I'll figure that out before Wednesday. And then we'll talk a little more about the final exam, and we'll be done on Wednesday. Questions? Any last thoughts? Okay, so between now and Wednesday, there's no homework, just study for the final. Good? Okay. All right, let's end it there.
Thank you.
See you later. Bye.
Thank you.
Thank you.